It's a pleasure to have Pratik here. Pratik did his PhD from Leiden Observatory under the supervision of Hugh Rodgering, and from India, Ayuka Jaideep Bagchi. And after that, he did, because of the pandemic, he joined Paris Observatory remotely. So he worked from India for some time. But a couple of months back, he has physically joined Paris Observatory. And we are glad to have him here because I and Pratik have worked together in India also. So thank you, Pratik, for coming and giving this good talk. Over to you.
Okay. All right. Thanks, Shishir, for the introduction. And thank you for inviting me and having me here. It's quite an honor to come here and present my work. So I'll be talking about some special kind of radio galaxies, which we call giant radio galaxies. So I'll get to in a minute why they are giant and why they are so fascinating. So short list of my some of my collaborators with whom I have worked for a couple of years on various topics exploring the aspects of giant radio galaxies. So I'll introduce radio galaxies and giants, the open problems they present, the project which we started to address these problems, and the results which we have got from various radio optical survey, and what work we have done with the subsamples using all the multi-wavelength data, and then some focus study on interesting sources and what future prospects are there for us to explore. So some of you may know what are radio galaxies, but just I'll give us a short introduction. You know the optical galaxy as we see looks like this and has an extent of 10 to 60 kiloparsec. Whereas when you see a radio galaxy, there is a multi-wavelength cartoon of such radio galaxy where you have the galaxy with the AGN at the center spewing out these massive jets and often terminating into big lobes, radio lobes and hotspot. So we have two main distinctions, the FR1 class and the FR2 class, Canora-Filey, our named after them. So in FR1 you see center brightening, you see very prominent core and radio jets extending outwards and fizzling out. Whereas in FR2, which are more powerful type of radio galaxies as well as population-wise more dominant, so you see hotspots at the end. They are edge brightened. Classically, that's what they were called. So this overall sizes, as you may have guessed, they extend quite more than what we see usually in the optical domain. And this is just a comparison chart. And the ones which we are interested are the giant radio galaxies, which are on the scale of megaparsec. So this particular radio galaxy is Hercules A. It is actually not a giant, but just for showing you illustrative purposes, I've shown you we'll have to stack more than 30 Milky Way galaxies to get to 1 megaparsec. So these are really massive galaxies, massive scales which we are talking and dealing with. And in AGM in the late 80s, early 90s, this kind of unified models came along, which tried to argue that we see various classes of these AGMs based on the orientation. Majority of the evidence is for this kind of model, but there are some questions which are still being explored about how good this particular model is. So in this we have a black hole spewing out jet surrounded by a dusty torus. We have good amount of evidence that this torus does exist, and depending on the viewing angle from where we are viewing them, we classify them into radio galaxies, quasars and blazars. So blazars are the most variable form Doppler boosted emission which we see, and they are quite viewed at a very smaller angle, like 0 to 10 degree line of sight. And then if you go on increasing, we have these other. This is just a very brief overview of this AGN model, unified AGN model. Now, radio galaxies come in various shapes and sizes, and radio astronomers have very nicely named them as per their observed morphology. So we have when we have a C-shaped, cup-shaped morphology, they are often called the wide-angle tail, narrow-angle tail, X-shaped, and so on. But what we are interested here are the ones called Giant Radio Galaxies. So these were originally discovered in the early 1970s, and these two were quite massive, and hence it was possible to detect them even with the technology back then, which was just developing. Remarkable results are there, and today we have imaged them further along with new telescopes, and we have a much better picture. So this is an illustration by Storm and Wiley and others in Scientific American, where they showed the comparison, the scales of these galaxies, the sheer big size of these galaxies. And I have taken the liberty to update it slightly with more examples which we have gathered along the years. So, to define giant radio galaxies, these are something which we which extend more than 700 kiloparsec from end to end. Okay, so from radio images, we are able to measure their angular sizes, and using the optic redshift of the host galaxy, host AGN, we can then get its projected linear size. We don't to get their inclination towards us, we will need the very high resolution VLBI observations, which currently are not done for this class of objects, so that we know the inclination of the jets, and then only we can deproject it and know their actual true size. But projected linear size is something which is close to the actual linear size, and that's what we go along with. So, they are mostly defined as something which are greater than 700 kiloparsec. The biggest one is about 5 megaparsec found till date. Mostly they are hosted by giant ellipticals, very rarely in spirals. And like I mentioned, the FR2 is dominant in radio galaxies, even in dominant population. And that's it. The same thing goes for the giants. And their spectral ages, how long they have been emitting, is of this in this range. Although this has been done for very handful of giant radio galaxies. And of course, they host the largest astrophysical jets, sometimes going out to 300, 400 kiloparsec, and eventually terminating into such structures. So, owing to their big sizes, often it is asked, do they possibly contribute to other large-scale processes? Are they responsible for perhaps seeding electron population for other phenomena which we observe? So they are most likely a good candidate for something called as the radio relics, which are associated with the merger of two galaxy clusters. So whenever such a merger happens, there is a shock which goes out, and it is often traced by the radio band. So what you see here, these two arcs, two sets of arcs, they are radio relics. So and these are also on the scale of megaparsec. So they would require the seed electron population or a seed radio galaxy of quite a big volume for it to get compressed by the shock and then expand. So, what are the open problems about giant radio galaxies? We are trying to understand why they are so big. Are they really rare? How do they contribute to the other processes which are going on? Are they just older counterpart of normal radio galaxies? Do they have a very short duty cycle, restarted activity, allowing them to grow and grow for larger distances? And what special parameters or what processes are governing its stability of the jets for such a longer time or scales? So is it a powerful AGN which is continuously being active and accreting, giving out this jet, or is it just that they grow in sparser environment, allowing the lobes to move more freely? Or is it a combination of two? So these are the kind of questions which we try to ask when starting this project, and perhaps we will be able to solve it using multi-wavelength data of studying its AGN as well as the large-scale environment. And for that, we needed a large sample of giant radio galaxies. So the way forward was use existing and the new upcoming surveys So LOTS is a survey with a low frequency array, which is mainly in Netherlands and now spread across Europe, which operates at 150 megahertz and below. And we need to use these kind of surveys to find more and then perform the study in an orderly fashion, going from AGN to large scale structures. So hence we started this project called SAGAN. Nothing to do with this great man Carl Sagan, which most of us will know. And but it's acronym which I coined Search and Analysis of Giant Radio Galaxies with Associated Nuclei, so that we study its all properties. So these are the goals we set out to carry this kind of study. So first was to make a complete compilation of all the known giant radio galaxies, because we knew there are not so many known as opposed to the radio galaxies. Radio galaxies have been known since the 1950s, and we know thousands of them, but very few were known. Giants were known. So first was to look through the compilation literature and make a complete compilation using a uniform cosmology, because in 70s, 80s, different H0 Hubble constant of 50 or 100 various were used. And recently with measurements from Planck and WMAP, we have more better constraints. So it was supposed to be done very uniformly. Next was to search using old and new radio surveys along with the upcoming optical facilities, and then study its AGN properties. We take the catalog, make subsamples, divide it into various redshift bins, and then of course follow it up in the radio and optical domain to get their properties like their ages and the densities around which they grow. So there are some of the telescopes which we have used in this kind of study. IRAM for studying its carbon monoxide, the fueling properties, LOFAR survey, GMRT for the spectral aging, they're doing the radio ages, and BLA, that's the main telescope which provided us 3 radio surveys to use. So this is how we stood back in 2016 when we started out this project. And this is just showing you the number of giants each year, how we knew. And the number was around only 300 or so. So let's go to the first task which we undertook, so compilation. And that was not an easy task, because we had to go through the EDS and search for various sort of names associated for this, because there was no practice of naming it then giant radio galaxies throughout. People chose their own kind of names, so it was very difficult to know and not miss. But we tried to do our best job, and these are the main keywords which helped us extract things from the literature. And then we verified its structure post redshift. By structures, I mean the radio structure, because in 70s, 80s, the resolution was poor, and often there were mixing of sources. So with the new data, we could verify those structures and weed out the problematic galaxies. So again, like I mentioned, we need to measure their angular sizes uniformly and probably using the same cosmological parameters. And the ones above 700 were classified as giant radio galaxies. So we continued this for nearly 4 years. So next was, now that we have the catalog, we can now do this search for finding more, because we know the 300 is very less, so we need to find more. So we had to do this because we had to do this manually. We have to take the radio maps and go through them one by one and find any extended structure, and then probe where is the host galaxy, what is the redshift, measure its sizes. And you can see the structures are not so linear, not so symmetric. They can be various shapes and sizes. So you can't employ immediately machine learning or some automated tools to do this. So it had to be done manually. And we used the latest optical surveys, the data from SDSS, which helped us. And in that fashion, it took time to do things because it was manual. But it was more thorough, and we are very sure about the results which we have. And that's the brief summary of radio survey, like what I told. It gives a wealth of data. This is a very rough sketch of various surveys which are present. It's a large sky coverage survey and the resolution. So this had to be used in conjunction with these optical and mid-IR surveys, which helped us identify its host as well as get the redshift, which is very important for us. So results. So we carried out this survey of part of the sky, 424 square degree. This is the first LOFAR survey, and we used that data to find giant radio galaxies. So this was one of the first very sensitive radio surveys to date, giving us 5 arc-second resolution and very deep sensitive maps. This is the head deck area. So this is covers 424 square degree. Low frequency radio are very useful because the effects of Doppler boosting are minimized at the lower frequency, and the radio emission is due to synchrotron radiation, and it follows the power law. So at lower frequencies you have more fluxes, and so it is easier to catch. And the diffuse plasma, which is often associated with these kind of galaxies, is easily traceable at lower frequencies. So hence this was an ideal survey to search, though it was from a very relatively small part of the sky. And as a result, we found some 225 new and overall 239 giant radio galaxies just from this small part of the sky. So which told us that they are not that rare as we initially thought of, but still they are not as common as radio galaxies either. So this is a montage of all the 239. So Shishir helped me create this beautiful montage. And there is a inner some snapshot of the structures which we were able to unveil, because this kind of emission very diffuse, which is only possible to be mapped with the low frequency radio form. So these are the double radio galaxies, which are the restarted. We see clear sign of restarted activity. You see the inner lobe and the outer ones. This is very diffuse and faint, and only with LOFAR this could be. No other survey is able to detect this currently. So you see the past activity here of the AGN. So there is a very visible recurrent activity. Not all recurrent AGN manifest this kind of morphology, but this is one way to know what kind of restarted AGN looks like. And here are the examples for hybrid morphology, that you have one side FR2, the lobe and the hotspot, and one side you have FR1, just the jet going. So we don't know what causes this kind of thing. It is conjectured that there is a different environment on either side giving this kind of, but we don't know for sure as of now. So there is the Nra Venus Sky Survey, which is a much bigger part, covering almost 80% of the sky. So obviously we had to use this. It gives us more scope, but it has a modest resolution, but it's quite sensitive at the same time. So we use this in synergy with other available radio surveys like the TFR GMRT Sky Survey. So this is again done at 150. It is shallower than the LOFAR one, but it covers almost 80 to 90% of the sky. So it has been very productive. This came out in 2017. And as a result of this pilot result, we found some 25 or so. This was before the LOTS search. And like I mentioned, we used the NVSS, which is a 1.4 gigahertz survey with 45 arc-second resolution, and we used the other surveys because they had a similar sky overlap. So this various resolution allowed us to get to know its other structure, which are missed in this particular survey. So this was all complementary, and then we used it with the HDSS, Pan-STAR and WISE for the optical and various database to get its redshift. And this is just a classification of what we used from the Proctor sample, which is a sample created by somebody called A.D. Proctor, and he basically applied his automated algorithm on a survey like NVSS and gave all the structures which are greater than 4 arc unit. So they were just candidates. Many of them turned out to be, nearly half of them turned out to be something totally different, even supernova shells. So that led us to find another large sample, so of 162 giant radio galaxies. So now, using this goals of the project, we were able to find two large sample of giant radio galaxies, 225 from the LOFAR, and then from this 162. And as I mentioned, when we started this project, we had only 300 or so. Now we have more than double of that. So this is again a montage of all the 162 giant radio galaxies. You can see the resolution is quite modest because these are NVSs, not LOFAR, which we are trying to now map slowly. There is a rough all the 820 that catalog. We combine all the literature and our findings into a giant radio galaxy catalog of 820. So this is the largest catalog we have till date of complete compendium of this kind of sources. And this is a sky plot. This high concentration is due to the LOFAR survey. So this is how things look now that we have found more using the NVSs in the lots. Now that we have this catalog, let's move to the third part. That's like we can create subsamples and study their host to identify what is so unique in their AGN and how compare them with radio galaxies and see what is the similarity or dissimilarity. So we could now ask this question: what is the space density? What kind of accretion mode their AGNs have, and how they vary from normal sized radio galaxies. So this is the SAGAN one, which has a result of all the study we carried out using the GRG catalog of 820 sources. And these are the properties which we were able to compute. So we used all the possible data which was there in the public domain without making any new observations. So with radio, we could get the radio power from various survey. We could get its spectral index. Spectral index is a measure of, it tells you how old the source is or how active the source is, but it doesn't exactly give you the spectral ages, but it's an indicator about the radio plasma. And we were able to classify their morphology, black hole mass, the Eddington ratio of the AGN, and classified its quasar and the ones which are located in the clusters. So, like I mentioned, this was all done using the publicly available optical and radio data. So this is the redshift distribution for our study. We considered only the sources below redshift 1, so because there are plenty, and we didn't want to get into the whole evolution business. So we tried to, and this is where most of the data was again available with SDSS. So, like I said in the start of the talk, that many thought that perhaps their accretion mode is different giants. We found that not to be the case later on, but let me just give you a brief introduction to this, whatever I mean by accretion mode and high excitation. So when you take the optical spectra of this AGN, you see in some you see very prominent emission line, and in some you don't see prominent emission line, but just a featureless spectra. And based on that, astronomers have been able to classify them into high excitation and low excitation. And then various models were given to suggest what kind of processes are governing this. And some even have said that AGNs sometimes start in the higher state and then eventually move down to the lower state. And here various models suggesting the efficiency of the disk are also associated with it. And in the recent time, Durkhan et al. And others have used the mid-infrared color diagram to differentiate this kind of AGN based on their location on this kind of line. So a priori from the optical spectra, they knew what kind of AGNs these were, and then when they placed them on a color magnitude diagram, they found that the low excitations preferred to be here, and the high excitation quasars preferred to be here, and star forming to be here. So this was followed up with more studies, and it was kind of established. So we used this because getting optical spectra for all the 820 was not possible. So we had to improvise with the, and WISE is a mid-infrared survey of the whole sky. It was a space-borne telescope. And we found that most of the AGNs of giants are low excitation, but considerable fraction is also in the high excitation. So clearly we established that they don't have a preferred accretion mode. They are high as well as low. Then we compared them with the quasar, because about 20% of the 820 sources were hosted by quasars, which initially was thought could be more rarer, but now we have that statistic. So we compared their properties, like whose sizes are on an average bigger, their radio power. So quasars, as expected, are more powerful than the radio galaxies, having more jet power and more flatter spectral index, which means that they have a very strong recurrent activity which is going on, keeping their spectral index flatter. Okay. This indicates that there is more diffuse part in diffuse old plasma in the radio galaxies compared to the quasars. And then we classified high excitation, low excitation, and studied their properties in comparison, size, power. So the high excitations were more powerful, high excitation AGN giants, more powerful in terms of their jet power and other properties. And their Eddington ratio was again more high. And if you compare them with the quasars have even more high ones. All these properties were not known before, and now we know what kind of distributions they show. And hosting the conjecture of GRGs hosting a more massive black hole and accretion activity, that also could be tested, and we saw that the black hole, the distribution of the black hole mass is more or less the same. And if you increase the statistics, I think we'll see more similarity. But there we are limited with the number. This was done using SDSS velocity dispersion data, M sigma correlation. And here we see the distribution is not so similar, but again, the statistics is low. So my hunch is that if we get more number, this might change. But as of now, yeah, this tail is empty for giants. The causes for the jets is often governed by this something called as the Disjet Coupling. You have accretion disk around the black hole, which is spinning rapidly and giving out this radio jet. So this, how strong is the Disjet Coupling? To explore that, for the giants case, for the cases we had the Eddington ratio, we plotted against Eddington luminosity normalized jet power and the bolometric, and you see a reasonably good fit to this kind of. So this acts like the indicator for disjet coupling. And there does seem to be a connection between these parameters. Now, before I get to the fourth part, let's slightly jump to the environment, which was another conjecture given to explain this giant radio galaxy, but nothing was done. These were just something people just said, okay, that could be the case. But now with the big number of sources in our catalog, we could really test this. So once we had the catalog, we used the cluster catalogs available in literature and simply cross-matched them, and found that about 15% of the giants were hosted right at the center of clusters, galaxy clusters, telling us that they do grow in denser environment. Right at the BCG, brightest cluster galaxy, they are the brightest cluster galaxy of the. However, they don't grow in very massive clusters. Okay, so that's how we got this statistic. So we can't really say that they just grow in sparser environment, because then explaining this 15% becomes difficult. So perhaps it's a more subtle things which are happening, and we do see that the effect is very much there on the morphology, because you don't see very symmetric nature for these kind of sources which are residing in the galaxy. So our study was limited to this kind of work, but I'll get to this towards the end.
Maybe I want to ask about clusters. Which cluster example you used, or how you found clusters?
Okay, so we use WHL cluster catalog and GMBC cluster catalog. WHL stands for when, how, and land. They use the SDSS data, all the data from, and they have a cluster catalog of 100,000 something, right?
130,000 clusters.
And then there were other two catalogs like GMBCG, which are from the same part of the stack. So we use those, and that is, it has a completeness up to 0.55 redshift. So when we compute this statistics, 15%, we only consider giants which are up to that redshift, not the whole.
Clusters, one of those would be rich groups, or
It could, yes. So yes. So there are few studies which have tried to show it via simulation. We actually searched that in terms of mass, what is the cutoff for a group, for definition of for a group and a cluster. So we found some papers giving out as 0.7 into 10⁻⁴ as MSEN, as the demarcation for galaxy group or cluster. But again, that's just few studies which have just shown it, tried to show it via simulation. So yeah, we just use that kind of, but clearly they are not found in very massive clusters. Okay, then from large scale structure to the region property, that perhaps they have a very big reservoir of fuel from which they are able to accrete and continue their recurrent activity. And we needed to see this via some possibly detecting some carbon monoxide using millimeter waves. So we tried to get data from this IRAM 30-meter telescope, and that was not easy because the selection criteria is very tricky. But we tried to get data for a 12 sample of 12, and fortunately we had selected a very oddball giant radio galaxy which is hosted by a spiral, which is very rare. There are only 5 such examples to know till date, and this is the most massive one. It's a clear spiral giving out, which is giving 1.6 megaparsec jet, and this is what you see. It has a big carbon monoxide reservoir, gas reservoir, which is traced by this CO2 to 1 and 10. And we found significant detection in two other candidates and upper limits for the rest of the sample. Because telling us that mostly the giant ellipticals which host them don't have this kind of gas, or they have really low amount of this gas, and hence the low star formation rate for this. So this is still a work in progress. Now we are applying for more time to get to bigger sample. But it seems that the star formation is really low owing to their giant elliptical nature. And this is a study which is still it's under review, where we have focused the study only on the quasars, and we have compared properties of small radio galaxies, giant radio galaxies, giant quasars, and small radio quasars, and try to see what differs. And it seems that quasars outshine giant radio galaxies in the most of their properties. So hopefully this will be accepted soon, and we get to read the next one. Okay. So, We also try to do polarization study of this kind of sources, which is again very difficult. And this was used. This was done using LOFAR and NVSS, and we were able to. We took the LOFAR sample of 239, and about 37 of them showed polarization. Now, using this, we can put some kind of limits on the environment it is growing in, and that's the kind of number we have. They seem to be growing in less dense environment, but this we are talking of just this 37 and relatively weaker magnetic field. And again, so this tells us that this can be perhaps with more data can be used as a probe for probing the environment as well, not just study these giants, but also we can probe environment. There are studies by Malarkey in 2013-2015. Both they have used similar techniques to study the WIMPs and as well as get the dense environment properties. Now, like I said, I'll come back to the fourth. We also followed up in multi-frequency. So before we begin, let me tell you that following up of these structures at different multiple frequencies of radio allows us to get their spectral edges and magnetic field estimate of magnetic field strength inside these, and only 20 or so have been done so far. These are the most famous and well done studies. So hence I'm showing it here. It was done in the late 90s by Mack et al. And it tells you the spectral edges range in this. Later studies showed that there are giant radio galaxies whose ages go up to 150 mega years, 180 mega years as well. So they too were able to get a estimate of their environment, which was again on the lower side. So we also try to do this, and doing this takes time. So it takes a couple of years to gather multi-frequency data from 150 to 10 gigahertz, getting a complete coverage. And along with that, we not only are able to do that, we are able to also study these aspects. We can get high resolution images of the jets, how they are propagating, the polarization, and study these aspects as a potential. Okay. Now, just a snapshot of these some galaxies which we studied with GMRT. And now you can see at various frequency how the various structures can be seen. Okay, so these two are the most sensitive maps. You can see this diffuse plasma covering coming up. This is a survey data with poor resolution, but it becomes more apparent. Similarly, here you see this plume which is going up, which is not clearly resolved here. Again, an example of a quasar. So this is what I was saying. You observe them at enough number of frequencies so that we get this kind of curve. This okay. This various frequency and this is the flux. This is a synchrotron power law kind of thing. And when we see a break here, that's what we call break frequency. It helps us identify the spectral edge and the break occurs due to the synchrotron losses, and inverse Compton losses, and eventually this happens due to the cooling. So we were able to do this with the high resolution maps. You can actually get spectral edges and magnetic field estimates of various parts, and we also got these numbers in a wide range of magnetic field and spectral edges, going from few tens to 100 mega years. And sometimes we do see some turnover. I'll not get into this now. Okay. So like I mentioned, I'll talk about one particular giant, which was very interesting. So this is what we initially spotted in a low resolution map, and we thought it's quite peculiar morphology. We didn't know what is this? What is this so bright object here? Is it part of it or something else? So we followed it with GMRT, and this is what we found. A bright object was this. Here is the core AGN, and there's a 300-200 kiloparsec jet which is going and into this structure, which looks like this. So it's like omega shape, some sort of instability which is occurring. And like I've said, this is the core where the host sits. So there are many particular things about this Giant Radio Galaxy. It is hosted by a BCG in a cluster. It has really long jet terminating into this kink structure and very diffuse lobes. It don't have hotspot, traditional hotspot. So, and what is more peculiar is that after this kind of instability is recalibrating to feed this. This is independent, these are background sources, not related to. This is, we expected it to be very flat. By flat, it means flat spectral index, which means there is possibility of a shock, and wherever there is a shock, there is possibility of acceleration of particles. Like I mentioned, this is hosted by a BCG. This is the host, which is giving out the jet service. And we tried to get the member galaxies using red sequence method. Shishir did this and see the distribution, how it is growing. And this is what we see. It shows that it is tending to avoid denser environment.
So all the galaxies which are not, are they members of the same cluster? Or something?
So we got the magnitudes of all the galaxies around the source and employed this red sequence method, and that gives us that's an estimate of that these are associated to the cluster just based on the magnitudes. And this is some work which took us a lot of time because wherever SDSS was absent, we had to go and follow up with the optical telescope. Now, I can't go to VLT and big telescope and say, give us time, I need to measure the redshift. They will not accept it. So we have to go to smaller telescope, but dealing with smaller telescope is always difficult. It's a very beautiful site there. They have almost 200 plus clear nights for observation, but the instrument and things are a bit tricky to use. So it took us some while to obtain the optical spectra, and we have this study. So in southern sky, if more and more optical surveys are coming, this task will be used. It will make our life easier. And so the future looks promising with all these telescopes which are coming up, which will shed light on various aspects of radio galaxies and many aspects of universe as well. So and this will generate a lot of data, and how do we expedite this kind of studies is perhaps invest more into automation algorithms, or put more manpower. That's why we should popularize astronomy more. That's my belief. Or there's a way called citizen science, which many of you may be aware. Get the citizens interested more in science and these kind of projects where they're educated and at their level they can contribute to the data set. So this Radio Galaxies is quite famous going across the world. This is sorry. Okay. So this is an initiative from India, right at home, which is completely done online. We have thousands of volunteers helping us classify this kind of sources in here. So that's more or less the end of the talk. I came here with the motivation to tell you about this kind of work and collaborate with Shishir and others here who are expert in dealing with a lot of optical data in context of the cosmic web filaments. So people have not studied radio galaxies in terms of their large-scale environment in detail as a big sample. And the group here has been doing quite wonderful work with respect to this filaments of the cosmic web in general. So I thought I could come and discuss this kind of possibility, what we could achieve with your expertise and my expertise, and possibly tell the community that, okay, what kind of environment radio galaxies really grow in. So with that, I will end my talk. Thank you.
Thank you for the very interesting talk. As for your last point, affiliation. You Our friends in Finland, in Turku, try to do very much that. We have radio lobes and relation to. I have some questions, but I will ask.
Yes, about the offset, to say that 15% of the time taken of galaxies are in clusters. Is it a lot or not? Because if you take all galaxies, then about 10-15% of galaxies are in clusters. So is it something that we expect? And where are the rest of the time taken galaxies in this environment?
Okay, so this before we began, it was just a conjecture that they do grow. They only grow in sparse environment. We didn't know. When we did this, we got so there was a priori no known thing. Okay, the logic dictated that they preferentially go in sparser environment, but this does show them. Okay, now what to make of it? It's quite difficult. Maybe Shishir, you have something to add?
Actually, we don't know how many GRGs are there. So also this data sample, it is not kind of complete.
Complete. Yeah.
So whatever we have, the GRGs, 820 GRGs, we did it with this sample. Maybe when the second data release of lots, when it comes, which has bigger,
We can aim for the completeness.
we can increase the number of GRGs and then see how many. And this is just a simple cross matching of BCDs and the host of
They may be in different part of the cluster towards the end or this thing that we don't know. For that, we need to.
85% are in voids or in some.
we don't
know. That's why that's the whole
Something
game.
I figure.
Yes, that's what we have to figure out.
that work has not been done yet.
Did you also have somewhere a plot of the redshift distribution?
I think I understand. This is a subsample which we considered for the following properties. That the entire redshift, I didn't put it. It goes. The highest redshift is around 3.1. That's quasar. That's very.
You go back to the
Of the redshift 0.2 or 0.15, we have quite good understanding of the environment in slow made. One starting point of study this.
Yes. Yeah. So we have some sources here, so which we could.
I think it also depends on all of them have SDSS spectra.
Yes, most of them do. Yeah. Most of them.
I understood that every two galaxies are subsample of giant radio galaxies.
FR2, FR1, that is something intrinsic to all radio galaxies, not something for giants. All radio galaxies have these two classification, distinction, 1 and 2.
This is identical because I know I go to see or maybe the power of one of the pretty insects. She collected data on every two galaxies.
Okay.
That is from NVSS, right? That catalog was made from NVSS.
Yes,
Yes, NVSS component of.
Okay.
So that catalog has around 100 FR2 galaxies, so we can look at that also.
It could be more for search for giants. For the giants, right?
But those are just radio galaxies,
Really?
not giants. But
Could be used.
we can check.
but I is sure that there is no any choice.
There
We
are
are
no-
not particularly
Exactly.
but we can see.
yeah.
Sure.
Anna, and before that, I also say that those who are listening remotely can also speak up or write their questions to the chat.
Well, I wanted to ask first the terminology. When you say that this giant radio galaxy, you mean the whole structure, like with no observing?
end to end.
Okay, but is there like can you make any comparison of the galaxies, like the normal radio galaxies and these giant ones? Are there big differences between these mother galaxies?
So, okay, I understand your question. So, we try to look at their AGN properties, AGN which is residing in the galaxy,
Yes.
not galaxy properties. As if you see this, so you can you see we have this magnitude of the galaxies, which are brighter, which are their properties of radio galaxies, radio galaxies and giant radio galaxies. The properties are more or less the same. The galaxy properties, post galaxy properties, they don't differ much. Okay, so we think it is mostly to do with the accretion state in which the AGN is, and not in general. So the current evidence suggests that it is a combination of AGN power and the state it has. Currently, it is.
The giant radio galaxies, they are mostly hosted by
Ellipticals.
Not
giant,
large
not
ones.
larger ones.
yes, but that's even true for small radio galaxies. Only 5 radio galaxies, giant or non-giant, are hosted by spirals. Known till here. Only 5. Rest all are.
Those elliptical galaxies can they are galaxies are similar. I mean, if you have elliptical galaxy, as giant radio galaxy and normal elliptical galaxy, are those galaxies similar?
Okay, you are saying the non-radio ones. That could be compared.
I ask myself then. You were trying to say that the elliptical galaxies do not have gas.
Just carbon monoxide for the, I mean, very low.
Yeah, but is there still enough gas to power the AGN or?
Because the gas tells you that the fuel, that's the current state. Okay, where we see this giant ellipticals which are very low or no carbon monoxide kind of gas, which could mean that the activity has ceased or just stopped. It could mean that. Where we know there is active star formation as well as AGN activities going on. That's the 1 or 2 objects we see. But it may not mean that which are where we don't see. It just could be the activity has just ceased, and this thing is propagating outwards. So there are ways to nail down if the activity is very recent or not, but we don't have the data for it.
You said the very large is 5 megaparsec extent. How much time does this kind of structure take time to
So it's very difficult to know that first because we don't have the we would need to know the densities around which it is going. Few studies of few sources have suggested their the velocities at which they propagate range from 0.1 to 0.3 c. Okay, now that is difficult to nail down unless you do this monitoring of the radio jet at VLBI scales. By VLBI I mean very long baseline interferometry, in which you can see the knots of the jets move. You see a superlunar motion. Based on that, you can estimate the velocities at which it is moving. So, past 20-30 years of research tells us that on an average they grow radio galaxies, not giants. For giants, it's not done. It's roughly between 0.1 to 0.3 c. So,
by the way, are those knots actually, do they correspond to actual physical motion or are they patterns?
they are physical motion because they have been monitoring this over a period of 20 years. You can actually see it move. There are knots.
So they move exactly at the same speed of gas. They're not just patterns, for example, some recombination or something
No,
like that.
they are actually moving. Yes.
In these simulations, can you find like how much time does it?
Yeah, I mean, you can assume an environment, or you can assume a speed, and then just take how much time it would take for you to move at such a speed. That's it.
But how
how does this time compare, for example, the time scale which the central engine can change its state to whatever, and justify changing or I mean, we know from smaller scales on macro binaries that they change states, right? So for high and low states.
I don't have a number for high and low, from high excitation mode to low excitation. I don't think people have computed that with respect to these kind of AGNs. But the processes at AGN level, the simulations have shown can go on for giga year or more. And the time scale which we are talking about, spectral, from just based on spectral ages, we know they don't go beyond 220 mega years, 10⁶.
So then it does make sense to look at, to compare the current state of the central engine to this large scale structure, because the time scales are very long.
But there could be faded plasma which we can't see, which tells us that this was active for more than 200 mega years, which could tell us. So we need more sensitive radio observations as well.
Yeah, it's not a question, it's not a comment. In one of the last slides, it states that the jets are avoiding the denser environment.
Seems to be.
Yeah, but since half of the galaxies are in filaments, so we can expect that the Giant Radio Galaxies become then more often filaments. So my hypothesis is that the jets are avoiding the filaments, so they're going perpendicular to the filament.
Could be.
Something that would be interesting to see.
Yes,
whether
yes,
that's true or not.
certainly. Yeah.
We know that they shift that for the two galaxies and
Depends on the sample size.
it's 120% of the size, and then the quantity that you have kilometers can be very long also, tens of megaparsecs. One has to look not at the many kilometers, but at that point where it really some kind of local environment.
No, it will be interesting to start with the giants because they are quite big, and then go down to smaller scale radio galaxies.
Well, I mean, when I speak about large and small scales, it is always useful to say what exactly we mean by that, because for some people, I know that typically people speak about galaxy environments, their small scale or local environment is really neighboring galaxy. Global environment may already be so split or clustered. Typically, when we are talking about global environment, this is something much bigger.
Yeah. So it will be fantastic to know if they have a preferred
But
quantum.
that the giant galaxy which you observe and you was cool or was cluster, at which age is this cluster was?
The one example I showed you, that's hardly 0.1. This one what I showed, that's 0.1 redshift. It is not far.
It's actually a group.
It's not a massive cluster, yeah.
It's a group.
This one, yeah. So this is at redshift 0.1. Now, we don't know if this is the best way forward, but this is what we try to do given the data we have. I mean, we didn't have spectroscopic measurements for all these. That's why we had to rely on optical magnitudes. Okay, so this is this is usual RA deck.
Yes, but I don't see the number.
Oh, sorry. Yeah, we didn't create for this thing. No, we're just publishing this, so I'm not giving. I didn't put the RA decks of this thing.
Can you go back to the polarization map which you showed? So, how did they measure the environment?
They assume equipartition. you assume the lobe density as opposed to the other. They are in equipartition, so you know the lobe density, so you can just put a constraint on that.
Did you like put the Doppler effect also, Doppler boosting, because
This was done using low frequency, where it's minimized. So hence it was. Any questions online?
doesn't seem to be.
I was not clear about it. You said that at low frequency Doppler boosting is
The effects are minimized.
are minimized. Why is that? I mean, Doppler boosting affects all frequencies the same, right? In principle, but you're saying that the environment where the lower frequencies come from are already decelerated, or what's the argument?
Okay, so the way I understand is the Doppler boost is boosting the emission, overall emission, which we are seeing. Okay, but at low frequency, you are more prone to seeing the diffuse plasma. Okay, so I think that's I don't get I don't remember the exact equation which is telling us, but the overall effects, because in at least in the synchrotron regime, synchrotron plasma regime, yeah, you see more diffuse. So I think there will be a frequency dependence, right?
For Doppler boost, no.
Because
I mean, if you have the same material moving the same way, let's say towards you, it doesn't matter what.
no, it's the cooling. It's over period of mega years, the whole plasma is also cooling. There are losses as well.
Yes.
And what we are picking up,
yes,
and what we are picking up at low frequency is the older part.
Yes.
At lower frequency, we are picking up the older diffuse part, not the most brightest part. So that's why the effects are minimized. You don't see the most Doppler boosted emission.
So is that it's the picture that basically, if you look at high frequency, you still see the jet that's moving relativistically.
Yes.
And if you look at low frequency, you see the lobe that already accelerated, and you see the additional many parts moving at many frequencies.
Because the higher frequency, that's going to show you more of that.
Okay,
That's the. Thanks for asking.
You are still.
Yeah, I'm here.
Couple more days and
yes,
continue the discussion. So, well, thank you very much again for this.
Thank you.
Next week's seminar is at 4 o'clock at the time of the space technology seminar on our activity. Thank you.